Okay, looking at today's, I already did the warm-up. I'm not going to go over it just because I think that's going to take more of our time. So, it's kind of how the answer keys here, it was working with our exponents. But we're going to just get into today's lesson. So today's goal is I can model and graph exponential decay functions. So we're going to do decays. Once again, yesterday we did growth. When we did our growth, we said b had to be bigger than 1. Well, in today's, b is going to be less than 1 but bigger than 0. So 0 is less than b and b is less than 1. The picture of it, when we draw this, decay is going to fall from the left to the right. And you'll see what that's going to look like. First thing, tell whether the table represents an exponential function. If so, write the rule. Okay, so we look at our x, and we see it is going up by 1. That's good. Now we have to look at our y. How is it going from 25 to 5? It's dividing by 5. Now, we are not going to write it as dividing by 5, though. We want to write it as a multiplication statement. So instead of saying divide by 5, I can say multiply by 1/5. Good. So we're going to say instead we're going to multiply by 1/5. If we look at this, what is our a? What would have been our y-intercept? 1. Why? Who said 1? Why was it 1? Good. Our x is at 0, so that shows us where our y-intercept is. A is 1. B, and remember, since this is multiplying or dividing the change, that means it is going to be an exponential. So B is going to be 1/5. We write our equation. Y equals 1 times 1/5, 1/5 in parentheses, and put it to the exponent of x. Why did I have to make sure to put 1/5 in parentheses? Maddie?
Just so you won't have to multiply it by anything else, and that's the first thing that you do.
Part of it.
Because you don't just want to multiply the 1 by x.
Good. If you would write your answer like this, that means the numerator is the only one with the exponent. But when I put 1/5 in parentheses, the numerator and denominator will get the exponent of x. Now, do I have to put the 1 in?
No.
No. So I would really write this answer as y equals 1/5 to the x exponent. Okay. And remember, our exponent can be any number we're putting up here for x. If I wanted to know in this table what the 13th term was, then I put 13 in for x, and I do 1/5 to the 13th power. That would be huge. So let's get right into this and start graphing, because it's kind of the exact same thing as yesterday. Making a table is important to helping you with your work. So on this one, y equals 1/2 and all to the exponent of x. What is going to be my a? Right away, we should know it is 1, because it's not listed, so we know it's 1. If we put this in, I could say, okay, if x is 0, my exponent is 0, I know it's 1 because it's like 1 to the 0 power, 2 to the 0 power. And anything to the 0 power is 1. Okay, what if I have 1/2 and I'm going to put it to the first power? What would be our answer? 1/2. Okay, we're going to change it and put 1 over 2 to the second power. 1 to the second power is 1. 2 to the second power is 4. So we have 1/4. Doing the positives are pretty easy. Let's make sure we understand the negative. 1/2 to the -1. I would show all my steps. Okay, I'm using -1 because that's my exponent, my x right here. When we have a negative exponent, we reciprocate. So this would be 2 to the first power over 1 to the first power, which is equal to
2.
and then I have 1, and we're going to the -2 power. So you'd write as 2 over 2, or 2 to the second power, 1 to the second power. This would equal, would equal 4. Now that I have my points, my table, this is why making tables so important, I can graph this, and it's pretty simple. It's just regular graphing. 0, 1. 1.5. I go 2 over and I go a 4. Will I ever hit 0?
No.
No. We're never going to hit 0 on this one. -1, 2. So -1 up 2. -2 up to 4. Now I have my points, and I just need to make my curved line. Our graph is going to look like this. This is going to be our decay. Now, the reason this line's going up more is we're seeing, like, just look at the space between your dots. How it's getting bigger and it's going faster. The next dot, if I want to do to the -3rd power, would have been 8. So then it would have been 5, 6, 7, 8. It would have been right up here. And then the next one would have been at 16. So I'm going to start seeing big growth in between my points. That's why my line, when I start getting here, gets steeper.
So for the table, couldn't you just do like one side and then make it either that number, the denominator under 1, or you could take it from the other side and just make that number 1?
On this, yes. But if we have another number of times, it usually comes out a little different. You'll see. Okay, this is decay. Because as we went from the left to the right, our number was dropping and getting smaller. So this shows the decay. Multiple graphs. This is the one that, once again, kind of like yesterday, so we're going to be comparing here in a second. So, first, graph y equals 3 times 1/2 to the x power. And we're comparing them. We want to compare all of them with this one. So when I give you my answer, whether it's a vertical stretch, a vertical shrink, a reflection shrink, a reflection shrink, if I say any of those, it's compared to this first one. So I'm going to graph this one first, my parent one. This is the one I'm comparing to. Y equals 1/2 to the x power. Can anyone tell me what my a is going to be automatically? We know right away. 1. Because we don't have that other number being times by my b. But I'm going to show the work for this one right here. So if I have 1/2, and we're going to put it to the, oh, here's this one, sorry, 0. So that's the first power. That's a horrible one. But let's put it to the first power. That's going to equal 1/2. What happens when I make the 1/2 to the second power? We get what? 1/4. Okay. We're going to go to this one now. negative 1. So I have 1/2, negative 1, negative 1. That will come out to 2. Negative exponents, so you reciprocate them. And 2 to the first power is 2. And then the last one, negative 2, so 1/2 to the negative 2 to the negative 2. We reciprocate those. 2 squared over 1 squared is 4. So let's use black. I'm going to use black on mine to graph my parent one, the one I'm going to compare it to. So 0, 1, 1.5, go over 2 and go to a 4th. Go negative 1 to 2, and negative 2 to 4. Draw my line in, something like this. Okay. I'm only going to start with this next one, and then I'm going to have you guys kind of showing your work and we'll compare. But I'm going to do my work down here. So for this next equation, I'm going to have 3 times 1/2 into the exponent. Well, my exponent, if we start with 0, 1/2 to the 0 power is still going to be 1. So then I do 3 times 1 is 3. Now, I could show you guys, there's one way to shorten your work a little bit. Since we did a 1/2 up here on this first one and we're doing a 1/2 here, it's going to come out that same thing every time. I don't have to do this work every time. I'm just going to times it by 3. So if I'm doing this equation and I'm doing 1/2 to the first power, 1/2 to the first power is 1/2. We've already solved that. So now I just have to times it by 3. So what is 3 times 1/2? Huh? 1.5. 3/2. It's 1.5. When we do the second power, we've already done that. Y, or 1/2 to the second power is 1/4. So we do 1/4, and I wrote a 3 for a reason. I don't know why. And we're times that by the 3. And if you're confused, remember I'm getting the 3 because that's our equation right here. So that would give us 3/4. Now think about our number right here. We had 3, we have 1.5, we have 0.75. We're seeing it's getting smaller. We go the opposite way. -1. Here's our work right here. 1/2 to the negative first power gives me 2. So then 2 times our 3 is 6. 1/2 to the -2 gives me 4. 4 times 3 is 12. These are my points for the second equation. We graph them. 0, 3. 1 and 1.5. Let's see. 1.5. 2 and 3/4. -1 would have been 6, and that's off our chart. That's way up here, right? So we graph this. Oops, I missed my dot. That's okay. How does this first graph in blue compare with our black one? Vertical what? Okay, Reagan thinks it's a vertical stretch. Is she correct? Yeah. Yes. It's skinnier than it. It falls inside. So I'm going to say vertical stretch. And we'll do the last one. Now this one, our equation was a little bit different. Our equation is negative 1/3 times our half to whatever exponent. So we're going to see how that changes it. I can still use my other work. I don't have to do extra work. On all of these, we have 1/2 to that exponent. Because of that, I don't have to redo all my work. It's actually silly to. So, when I said 1/2 was 0, that was 1. So I'm going to do a negative 1/3 times negative 1/3 times 1. Does everyone understand? I want to make sure I'm not skipping anything on anyone. Do you get why I'm not redoing the work? Because you would have to. If I had just this equation, I'd have to do 1/2 to each one of these exponents. Well, we did all that work right here. So I'm just using that to help me.
Wouldn't this one be the same as the last one? Because you would flip it because it's negative, so it'd be 3/1. So then it'd be 3 again, and then it'd be the same numbers.
No, because this is not, you're talking about flipping the negative 1/3 to 3/1.
Yeah.
But this isn't an exponent. We only flip it if it's a negative exponent. This is just negative 1/3.
But I thought they couldn't be negative.
Huh?
I thought they couldn't be negative.
Exponents cannot be negative. When our exponents are negative, we reciprocate them to make them a positive. This is just, we've learned that you can have a negative 1/3. That's okay. So now, my 1/2 to the 0 power is 1. So I'm going to do negative 1/3 times 1, which would be negative 1/3. Okay, if we go to the first power, the first power, 1/2 to the first power is a half. So now I have negative 1/3 times a half, which is going to give me negative 1/6. I have 1/2 to the second power. That gives me 1/4. So I'm going to have negative 1/3 times a fourth. It's negative 1/12. Do you see anything relating to it right now? Look at these three that we just did and compare it with this one. Here we had 3, 6, 12, negative 1/3, negative 1/6, negative 1/12. In your head, you should be already thinking, what do you think my graph will look like? Okay, we have the negatives to do. 1/2 to the negative 1 power was 2. So I'm going to finish out my equation. Negative 1/3 times 2 is negative 2/3. Then I'm going to see this one. 1/2 to the negative second power is 4. So negative 1/3 times 4 is negative 4/3. We're going to graph this now. I'm at 0 and I'm at negative 1/3. Negative 1/3, there's a half. It's probably somewhere right there. When I go positive 1, I go to negative 6. 1/6. That's about half the distance closer to 0. Negative 1/12. That's half the distance between those two. So I'm probably right in there. When x is negative 1, I should have negative 2/3. So that's like 0.6. That's a little bit bigger. When it's negative 2, it's negative 4 1/3. So that's 1 1/3. So I'm about here. and we look at it, what should this be compared to my black line, do you think? It is a reflection. Which part? Okay. Does the graph represent a growth or decay? If we look at this one, which one is this? It is our decay. What is our A? Good. We see that it crosses our y-axis right there, so it is 2. Now, to find our B, it's best to set up this table. If x is 0, and that meant my y was 2. This coordinate point, -1, 4. Oops. And I have these backwards. Why did I put these backwards? Okay. How do I know I had this backwards? Does anyone know? Real quick. I gotta go left to right. So when -1 is x, y is 4. 0 we said is 2. What would be my b? Yeah, we're dividing by 2, which means times by 1/2. My b is 1/2. How would you write this rule? Should be fairly simple. Yeah?
Y equals 2 times 1/2 to the x power.
That is your answer. Remember, do not multiply your a and b. So don't say it's y equals 1 to the x power. These stay separate. A is your y-intercept. So y equals 2 times your b is 1/2, and you're putting the exponent with that b. That's why you have to keep them separated. Oops. Okay, well I have the answer here for you already. I try sometimes. Okay, this is exactly like yesterday's. Biggest thing is make sure we are using this equation. And it's mainly fill in the blanks. You purchased a cell phone for $125. That, I know, that'd be
cheap cell phone.
I'd be okay with that. But I purchased it for $125. That's my initial amount. The value of the phone decreases. That tells me we're going to have a decay by 20% annually. So my rate is going to be 1 minus my rate of 20%, 0.2. And they want to know how much the phone is worth after 3 years. So every year, annually, it goes down 20%. My equation that you should have is y equals, the initial cost was 125, 1 minus 0.20, or just 0.2, and it's really to the t power. And that t stands for time. Now they asked for 3 years, so I replace t with 3. I would do 1 minus 0.2, give me 0.8. And then if I use my calculator, you'll see that we could do 0.8 to the third power is 0.512, and I'm timesing that by my initial amount. That phone, after 3 years, is only worth $64.
Whenever you put the 1, shouldn't it be a 1 plus 0.20?
Okay, The reason it's not is because this is a decay. Yep. Yesterday, if the phone was going up in value, it was like LeBron James's rookie card or something, and it goes up in value every year. Then you'd use plus. But when it's decaying, we're subtracting. And I think that's it. Okay. Your homework. Biggest thing on this, you'll see it's telling you, make a table. Make a table to help you. Even if it's like on this one, even if you do it just for 3 points, -1, 0, +1.